My dear students, I welcome all of you for today's session. Today's session is on mathematical analysis of recursive algorithms. In previous session, we had a discussion about mathematical analysis of non-recursive algorithms. And you know difference between non-recursive and recursive algorithms. You know what actual recursive algorithm is, right? An algorithm that invokes itself is known as recursive algorithm. Again, what actually we are going to study in this session? Okay, again the analysis of design recursive algorithm. You are given problem, now you have come up with a solution, and solutions recursive algorithm. So how efficient is your solution? I need to analyze. Okay, to analyze efficiency of your algorithm, what I need to do? As usual, I need to identify basic operation, and I need to count the number of times your basic operation is going to be executed. Okay, and that basic operation count is nothing but it gives time efficiency. Okay, lower the basic operation count, we say the best the algorithm is. Got it? So again here we have come up with a solution which is a recursive one, and we are learning how to analyze its efficiency. Clear? So now we'll come to the agenda of this session. So as in previous session, which was on non-recursive algorithm, okay, the same we are going to study here, but with the context of recursive. So first we'll see general plan. I mean, we have designed an algorithm, okay? So now what are the sequence of steps? What are the procedures I need to follow to analyze the efficiency of your algorithm? Here, the first three steps are same as mathematical analysis of non-recursive algorithms, okay? Whereas the next two steps are quite different because it's a recursive algorithm. So the fourth step here, we are going to set up something we call recurrence relation, not as summation. Okay. Next, as usual, we need to, once we have designed an algorithm, we need to identify the basic operation in that algorithm. Okay. We know what is basic operation is the most time consuming, frequently executing operation, frequently executing step in an algorithm. Okay. Then suppose some cases like what I said in case of linear search. Okay. The runtime of an algorithm not only depends on that size, it used to depend on some other parameters to say key element to be searched. In that case, we used to identify best case, average case, worst case. We'll see here also. Do we need to, is there only one efficiency, or we need to identify best case efficiency, average case, worst case? I will look at this. And finally, we'll apply this procedure general plan for some recursive algorithms. Okay. So now coming to general plan. As said, the first three steps are same as analysis of non-recursive algorithms. Clear? So first thing what you need to identify here is in your algorithm there may be any number of parameters. Okay, maybe a local parameter or formal parameters, whatever it be. So the first and foremost thing is that among the parameters, you need to identify what is that parameter that acts as size of the algorithm. Like in array, n is the size. In matrix, the order of matrix is the size, that is m and n. That is the first step you need to identify. There is the parameter that acts as size. The next step, you need to identify what is the basic operation in the algorithm. Okay. You need to there may be any number of steps. Okay. Among those steps, you need to identify that particular step or that particular operation that is most frequently executing, most time consuming. Okay, clear? So now assume you have identified the size, you have identified basic operation. Now check whether the execution of basic operation depends only on size. If it depends only on size, okay, you just need to determine the basic operation count. Suppose the execution of basic operation depends on some other parameters too. Okay, on some other parameters too, or some other properties. Okay, there may be a case we need to determine. We call best case, average case, worst case. Got it? So you remember, right? These first three steps are same as the first three steps of mathematical analysis of non-recursive algorithm. Now, what the solution you are given is a recursive. Priya, to solve a problem, you have come up with a recursive solution. Oh, so now in non-recursive algorithm, fourth step, what I said, I need to set a summation that gives the count for the number of times basic operation is going to execute. But since it's a recursive algorithm, I can't set up a summation. Okay. I need to set up a recurrence relation here. Here, I'm not going to set up a summation. Rather, I'm going to set up a recurrence relation, and that recurrence relation should represent number of times basic operation is going to execute. I repeat, here you need to set up a recurrence relation, and that recurrence relation, okay, should give the number of times the basic operation is going to execute. Clear? Also, this recurrence relation should have an initial condition too. This you will become familiar when I come up with some exercise problems. Clear? The first step is we need to set up a recurrence relation. And do you remember in previous session I said from your past semester subject, discrete mathematical structures, you need to recapture mathematical induction and recurrence relation. Okay, I repeat, go through DMS, discrete mathematical structures, and relearn recurrence relation as well as mathematical induction. Clear? So now, fifth step, what it says that once you have set up a recurrence relation with appropriate initial condition, and that recurrence relation represents the count for number of times basic operation is going to execute. Okay. Now you need to solve this recurrence relation, and solving this recurrence relation you have learned in discrete mathematical structures. Once you solve this recurrence relation, you will get the count for the basic operation. Once you have the count for the basic operation, determine what type of function is that. Once you identify what type of function is that basic operation count, okay, is it a logarithmic, linear, n log n, quadratic, cubic, exponential, factorial, you can represent that in terms of asymptotic notations. Yeah, got it. So now we'll come to some exercise problems. Okay, coming to first problem, what the problem statement? Design a recursive algorithm for computing the factorial of a given non-negative integer n. Then analyze the time efficiency of this algorithm. Okay, here what I said, what I watched, you need to design a recursive algorithm. Recursive algorithm is an algorithm that invokes itself, an algorithm that calls itself. Clear? So remember, you have studied in discrete mathematical structures. When I give a recurrence solution for any problem, there are two things. One is an initial condition. Initial conditions, why? So one, that further invocation of an algorithm should terminate. Okay, initial condition makes further invocation of an algorithm to terminate. Okay, the first and foremost thing, you need to identify what should be an initial condition. Next, you need to set up a recurrence relation. Okay, you need to set up a recurrence relation for the basic operation count. Okay, no, sorry, basic operation count I'll discuss later. Recurrence relation for the solution. Okay, first I'm designing an algorithm, right? So for designing an algorithm, okay, clear. So I need to set up a recurrence relation for computing the solution for the problem. In this case, I need to set up a recurrence relation for computing the factorial. Got it? For computing the factorial. Okay. So now remember, so we know that for negative integers, we don't have factorial. For non-negative integers, what is the first non-negative integer? It is 0. So we know what is factorial of 0? It is 1. So we were asked to compute factorial of 0 means you can directly say it's 1. Clear? So look at that initial condition. I said if n equal to 0, then fact of n is nothing but 1. Now what about recurrence relation? So suppose, let me say you want to compute factorial of 5, okay? So factorial of 5, you need to compute. Suppose you know factorial of 4, you just multiply 5 to that, you will get factorial of 5, right? Getting, I mean, you want to compute factorial of 5, but you know factorial of 4. You just multiply 5, you will get factorial of 5. Okay, so what I can say, now if n is greater than 0, means n is having a value other than the initial value. Okay, then what I can say, I can set a recurrence relation for factorial. Fact of n is nothing but fact of n minus 1 into n. Just now I said, right, you asked to compute fact of 5, but you know fact of 4. You multiply 5 to that, you will get fact of 5. Got it? So now if we have suppose just analyzing for a solution, if we have analyzed how to solve the problem, now I come up with the recurrence solution, and now I know what is my initial condition and what is recurrence relation. Got it? Now I can write an algorithm. So look at the algorithm. If n equals to 0, if the algorithm is invoked with 0, it returns 1. Fact of 0 is 1, right? Yes. Means n is greater than 0. Recurrence relation. Now, what I said, this fact algorithm should invoke itself. Now, if L in else, what you see, the algorithm is invoking itself with the argument n minus 1. So we call such an algorithm recursive. Clear? While invoking, it multiplies n. Clear with this? So now we have designed a recursive algorithm. This is our solution for the factorial. Now what I need to compute? Design an algorithm. Later, now I need to analyze how efficient is my algorithm. So in general plan there are 5 steps. What is first step? Identify the parameter that acts as a size. And what is that parameter here? It's nothing but n. Clear? First step is clear. Parameter n acts as the size. What is second step? I need to identify basic operation. So what is basic operation? Can anyone tell me in this case? So looking at the algorithm, I find multiplication is the basic operation. Multiplication is the basic operation. Clear? So I've identified the size to be n. I've identified the basic operation to be multiplication. So now it's very clear the execution of multiplication does not depend on any other parameters. Multiplication depends only on n. So here we need to just determine one basic operation count. Okay, determine basic operation count for multiplication. Now fourth step, what it says, I need to set up what? Not summation. In this case, I need to set up a recurrence relation for the basic operation. I mean recurrence relation for multiplication. Okay, so now let me assume, be clear, be cautious. Let me assume there is some function m of n is some function. Assume m of n. Have a look. Okay, have a look. Say look at a and b. Okay, let m of n be some function. Okay, and that function gives number of times multiplication, that is basic operation, is going to execute. I repeat, assume m of n to be some function that gives number of times basic operation. In this case, multiplication is going to execute. Clear? So now we'll come to algorithm. See, assume what I said, m of n is some function, okay, that gives number of times basic operation, multiplication is going to be executed. So now suppose, let me say, if n is 0, assume n is 0. Have a look at the algorithm. Have a look at the algorithm. Now assume n is 0. Tell me, any multiplication is going to be done? Is going to be performed? No. If n is 0, it's directly returning 1 to the invoker. No multiplication is being performed. So I mean m of 0. What I said, m of n is a function that gives number of times multiplication is going to be executed. So when n is 0, no multiplication. So what is m of 0? It's nothing but 0. So just now look here, initial condition. If n equal to 0, then m of n equal to 0. Got it? Initial condition. If n equals 0, then m of n equals 0 because no multiplication. Now we'll come back to algorithm. Suppose if n greater than 0, okay, have a look at the algorithm. Suppose if n greater than 0, how many multiplications are done? Okay, so we see if n is greater than 0, how many multiplications are done? we are looking at algorithm, we see there is one multiplication, clear? But you need to consider even there are multiplications involved on invocation of factorial with n minus 1. See, looking at the algorithm, we'll see at the return statement, we find one multiplication. Consider that one multiplication need to be considered. Along with that, the number of multiplications that will be involved when I invoke function fact of n minus 1. Got it? So now let me assume m of n minus 1, m of n minus 1 is the number of multiplication that is involved in execution of fact of n minus 1. Got it? So what is m of n minus 1? Number of multiplications involved in execution of fact of n minus 1. And for that one, we will have one multiplication. Clear? So I repeat, m of n, number of multiplications involved, right? When n is 0, we know return 1. So m of 0 is nothing but 0. When n is greater than 0, m of n is nothing but one multiplication more than the number of multiplication involved in invocation of fact of n minus 1. Okay, so look at the reconciliation. What I said, m of n equals m of n minus 1 plus 1. What is m of n minus 1? Number of multiplications in the execution of fact of n minus 1. And for that one multiplication I need there. Clear? So now I set up first step is very clear. Now I set up an initial condition. Now I also set up a recurrence solution. Okay. So now you need to solve. Okay. Now you need to solve this recurrence relation. Okay, and you know how to solve. You have learned solving recurrence relation in discrete mathematical structures. Solving this recurrence relation, I will find. Look at the last line. M of n equal to n. Okay. So what is basic operation count for recursive algorithm for computing factorial of n is nothing but n. Got it? So I've obtained basic operation count. It's n. Now what type of function is linear? So now also I know that this n number of multiplication should be done. Not even one multiplication less or one multiplication more. N should be done. So it is big theta. Clear? So now let me have a look at the second problem. Okay. Let me have a look at the second problem. Here it's a tower of Hanoi problem. Okay. I explain the objective. Here the question is that explain the objective of the tower of Hanoi problem. Analyze the efficiency of this algorithm. Now, what actually tower of Hanoi? I will tell you. This figure. See here. First, look at that figure. Okay, in the first row. Okay, there are some n disks. In this case, I'm showing just 5 disks on the source peg. The objective is that you need to move all these 5 disks to destination peg. But at a time, you can move only one peg from any. At a time, you can move only one disk from any peg to other peg. Got it? Clear? So now the objective of this algorithm is to move n disk from source peg to destination peg using an intermediate or auxiliary peg. Okay, at any time, no larger disk should be placed on smaller disk. And the number of disks n is the size of the problem. And here the basic operation is what? Don't get confused. We have heard about addition, subtraction, multiplication. But here the basic operation is moving a disk from source to auxiliary. or moving a disk from source to destination, or moving a disk from auxiliary to destination. The basic operation is moving a disk. And now here we need to determine how many movements of disk are there. That is the basic operation. Got it? And then we need to represent the efficiency for the count of moving a disk. Got it? So solution is very clear. Okay. Now look at this second row. I'll tell you how to design a recursive solution for this. So to design a recursive solution, just I have shown some like triangle, right? That triangle, which is almost triangle, represents the top n-1 disk. Almost triangular shape represents, that is a quadrilateral, almost seems to be like triangle, quadrilateral, okay? That represents top n-1 disk, below that there's one disk. So what is first step, what I have done? I have moved this top n-1 disk from source to auxiliary. I don't know how many movements are involved. Let it be m of n-1. Got it? I have moved top n-1 disk from source to auxiliary. For that number of movements, let it be m of n-1. Then later there will be only one disk on the source page, right? That can be moved directly from source to destination with one movement. Consider this one movement. Got it? First, I moved top n-1 disk from source to auxiliary. Next, I moved the bottommost disk from source to destination with one movement. Next, the n-1 disk which are on auxiliary, I need to move to destination. Let the number of movements again be m of n-1. Got it? So this is an algorithm. So first, see here. If n equals 1, if n equals to 1, there is only one algorithm. This is the initial condition. Sorry, if n equals, there's only one disk. There's only one disk on the source. I can directly move the disk from source to destination. So initial condition, only one disk is there. Number of movement is how much? It's 1. So m of 1 equals what? 1. I will look initial condition. M of n equals to 1 when n equals to 1. Because on the source there's one disk to move to destination, we need one movement. So otherwise, so what I need to do, if n is not 1, else part what I need to do? First, what I have done in this figure, top n-1 disk. I am moved from source to where? Auxiliary. So tower of n-1 source to auxiliary. Second step, I moved the bottommost disk from source to destination. Print move disk percentile D from percentile C to percentile C. This represents that step. So next step, again top n-1 disk from where? Auxiliary to destination. Tower of n-1 auxiliary destination. So recurrence relation for this is m of n equals m of n-1. What is first m of n-1? To move the top n-1 disk from source to auxiliary. And plus one movement is for moving the bottommost disk from source to destination. And again, plus m of n-1, that is to move the remaining n-1 disk which are on auxiliary to destination. So now solve this recurrence relation. So to solve the recurrence relation, you have learned how to solve the recurrence relation. You have learned in your discrete mathematical structures. Okay. So I set up 1 second, coming back. So see here, when there is only one disk, number of movement is 1. So initial condition m of 1 equals 1. When more than one disk, recurrence relation m of n equals m of n-1 plus 1 plus m of n-1. So m of n equals what? 2 m of n-1 plus 1. solve this recurrence relation. Okay, solving this recurrence relation and making use of mathematical induction. That formula summation I equals 0 to n minus 1 2 to the power I equals 2 power n minus 1. Got it? So I mean, solving this recurrence relation, okay, I'll come to know the basic operation count, m of n. That is the number of movements involved. Number of movements involved in moving and disk from source to destination using auxiliary is nothing but 2 to the power n minus 1. Okay, I repeat, the number of movements involved in moving n disk from source to destination peg using auxiliary peg is nothing but 2 to the power n minus 1. Got it? So now I have the basic operation count. So once you have a basic operation count, what you need to do? You need to represent it in asymptotic notations. So identify which type of function it's going to belong. Looking at basic operation count, it is very clear it's an exponential. It's an exponential. So now whether it's an exponential. Okay, now the question is that I need to represent it as big O of exponential or big omega of exponential or big theta of exponential. Here I need the complete 2 power n minus 1 movements, not even a movement 1 less than 2 power n minus 1 or not even a movement 1 more than 2 power n minus 1. I need same as 2 power n minus 1 movements to move all n disks from source to destination using auxiliary. So the big theta is the pop exact and big theta is the precise asymptotic notation in this case. Okay, so this is about recursive algorithm. Clear with this? So I repeat, what and all topics we are discussed in this session. One is general plan. Make a general plan for analyzing the recursive algorithm. Again, basic operation. I think everyone are clear with what is basic operation. Everyone are clear with identifying the basic operation, right? So remember, in fact, in a factorial problem, basic operation is multiplication. And in this tower of Hanoi problem, basic operations movement. You might have not wondering movement. Movement, is it an operation? Of course, it's an operation in that context. Got it? So next, what we need is the recursive. Since it's a recursive algorithm, here we need to set up a recurrence relation. Okay, for the solution as well as recurrence relation for basic operation. So while we set up a recurrence relation, very important is that we need to define an initial condition. Okay, initial condition is that one further invocation should stop. Got it? So then you need to clearly set up a recurrence relation, analyzing how you're going to solve it. Yeah. So first you set up a recurrence relation with appropriate initial condition for the solution. Got it? Design a recursive algorithm. Got it? Then you set up a recurrence on first you identify a size, identify basic operation. Next, set up a recurrence relation for the basic operation. Solve it. After solving, we have the basic operation count. That may be linear, logarithmic, quadratic, cubic, exponential, factorial, whatever. You represent it in terms of asymptotic notation. So to be which asymptotic notation I should use? Big O, big omega, big theta. Okay. See if what the basic operation count I got is maximum as an upper bound, then I should go for big O. If the basic operation count I got is minimum, lower bound, I should go for big omega. If the basic operation count what I got is same, exact, that number of times should basic operation should execute, then we need to go for big theta. Clear with this? So this is about today's session. Okay, thank you for listening. Let me wind up.